Our next presenter is Dr. Gerry Leisman, who is an Israeli neuroscientist educated in Europe and the United States in medicine, neuroscience, and biomedical engineering at Manchester University. Additionally, he received a PhD in neuroscience and biomedical engineering from Union University in 1979. He is currently a full professor and research fellow at the University of Haifa in Israel. Concurrently, he is professor of restorative neurology at the University of Medical Sciences in Havana, Cuba. He is editor-in-chief of the journal Brain, Body, Cognition. His scientific career has largely been involved since the early 1970s in the promotion of consciousness as a scientifically tractable problem, and he has been particularly influential in arguing that a fundamental understanding of consciousness can be approached using the modern tools of neurobiology and understood by mechanisms of theoretical physics, having, together with Dr. Paul Koch, developed biomedical applications of continuum theory. He has also been influential in examining mechanisms of self-organizing systems in the brain and nervous system applied to cognitive functions, exemplified by his work in movement cognitive interaction, memory, kinesthesiology, optimization, consciousness, death, autism, and developmental disabilities. He has likewise applied optimization strategies to movement and gait, cognition, and coma recovery. It is in this context that he was one of the first to identify functional disconnectivities in the brain and nervous system. He was elected Fellow of the Association for Psychological Science in 1990, a senior member of the Engineering and Medicine and Biology Society of IEE in 1986, and a Life Fellow of the International Association of Functional Neurology and Rehabilitation in 2020, having received its Lifetime Achievement Award in 2011. He has also served as a consultant to the U.S. National Sciences Foundation. So without further ado, Dr. Leisman. You're still muted.
I repeat again. Thank you so much for inviting me to our session at this particular point. I'm going to just very quickly review what Dr. Mayer said a little while ago, that we're dealing with a VUCA environment, which includes volatility, uncertainty, complexity, ambiguity, and hyperconnectivity. And yes, I am speaking in compressed speech because the time that we have together is limited.
Can you make a full screen? Can you do full screen on your computer?
Of course I can.
So it's small.
One moment. Let me just change the view.
Yes. No.
Try it again. Here.
Down. You have the screen down. No, down, down, down.
How's that?
Down, down, down. Down right. You have a screen. You see at the down part. Okay, leave it like that if you want.
Okay, no, this is fine. We can get through the content of what it is that we're trying to look at. The principal physiological effects of VUCA include the autonomic reactions, so-called autonomic reactions, which is increases in heart rate, fibrinogen level, which is blood clotting factor, blood sugar level, glucose, increased respiratory rate. These are the things that Selye in the 1950s actually referred to when he was describing stress reactions. I think we should probably make a point before we even begin, and we'll talk about it a little bit more in depth as we proceed, which is that we human beings are incredibly adaptable. In fact, adaptation is what was built into the system. In fact, the more adaptable you are, the more intelligent you are, actually, because intelligence can be defined in terms of either the number of trials to acquisition or how adaptive you are in novel situations. Different kind of intelligence. However, given the fact that we are adaptive organisms, why should there be a stress reaction? The answer is very simple. That is, Selye defined stress as anything that's perceived by the organism as being physically and or psychologically injurious to it over prolonged periods of time. So there's a time issue that's involved in our being able to effectively define stress reactions. Anything other than that is not stress, it's a stressor. And we, as adaptive organisms, are highly malleable and adaptive to changes in our environment. So let's give an example. We have political uncertainty. We have it here in Israel, and we certainly have it in the United States. I don't need to we have more than political uncertainty. We have a fair degree of uncertainty in the world. We can actually represent that uncertainty, the uncertainty reactions, in terms of specific areas of the brain, in particular the bilateral insula, which has a unique response to uncertainty. In fact, terrorism is really not a bad thing when you consider it objectively, which is there are a bunch of people. For example, we had this another Holocaust essentially here in Israel, where 1,200 people were murdered on the spot. But if you take 1,200 people compared against our population of 9 million, that's really not very many. I could say the same thing about the World Trade Center going back to 9/11, which is roughly a few thousand people were murdered on that day. And yet, in terms of the 350 million individuals in the population of the United States, that's really not that much. So what is it? What is it about terrorism that affects our resilience? And the answer, very simply, is uncertainty. It's a political uncertainty and has a direct response in the brain. What's that response? When we have ambiguity and threat in front of us, we have very specific pathways that can be mapped, and you can see them quite here. We have increased attention in hypervigilance, so the hypervigilance pathway is activated. We have problems with safety learning, which system shuts down. We have heightened reactivity to stress uncertainty, and so it goes. Very graphically represented in these particular slides. Which brings us to another issue before we can actually begin to put all of these bits and pieces together. And that is the difference between what we call small versus large world networks. Let me explain what I mean. When we are looking at a fetus or a newborn infant, or let's say a child through middle childhood years, what Freud used to call latency, I guess, we're essentially dealing with small world networks. And that roughly relates to what you learned in Psych 1 about the organization of the brain, which is the left hemisphere, the temporal lobes. The left temporal lobe deals with language, the frontal lobes deal with executive function, and so on and so forth. Unfortunately, it doesn't work that way. In fact, the brain actually organizes itself on the basis of networks. And these networks are the result of repetitive learning that allows us to behave automatically. Why do we need to behave automatically? Very simple. So we don't have to think about what it is that we do. Because the more you think, the more trouble you're going to get into. In fact, if you had to think before swerving your car when someone was heading directly at you on a potential head-on collision, you would be extremely dead. However, by being reactive but not cognitively reactive, you can avoid the danger, and then you worry about the emotionality later. As we get older, those small world networks change to large world networks, and so there are more areas, greater areas of the brain that are involved in a given response. So there's a fundamental change that's going on as we get older. If we were to look at this histologically, which we've done, we can see that in a 5-day-old infant, there's a paucity of connectivities in dendritic interconnectivities. In a middle school child, a child in the ages of kindergarten, kindergarten to high school, but not including high school, there are exuberant connectivities, and we can see the appropriate PET scans here, because the child is learning how to learn. He's learning how to put his world together. And we adults look closer to a 5-day-old infant than we do to a middle child. Why? Because much of what we have done is automated. So the bottom line here is that as a consequence of aging itself, and by aging, I mean from early childhood into adulthood, and by neurological adulthood, I mean in males roughly the age of 26 and females the age of 27, much of what we do in life is automated. So what can we say about that in the context of chronic stress? Very simply, what we can say is that chronic stress leads to dendritic shrinkage. We're going to be looking at an impairment in the ability to make new connections, which means we have a problem in the capacity not only to learn, but in to relearn. And by what we mean by relearn, oh, by the way, learning in Latin is habilitas. So rehabilitation is not fixing something that's broken. It's relearning something that was previously learned. We're going to have a significant problem in being able to relearn the skills that we had previously due to dendritic shrinkage as a consequence of stress. In fact, what we can say, as a result of the work done at the Center for the Developing Child at Harvard, that under normal circumstances, typical neuronal connectivities look thusly. But as a result of toxic stress, you can see clearly the paucity of connectivities between dendrites, which means that your capacity to learn new things, to make associations, is going to look more like a small world network in early childhood than it will in the adult network of automated behavior. Which then brings us to one of the very few laws in psychology, in psychological science, and that's Yerkes-Dodson, 1905. Basic idea here is that if you have too much stress, your performance level goes down. So too much arousal, too much stress, poor performance. Too little, poor performance. So we need an optimum level of stress in order to be effective in what it is that we do and how we handle dangers in life. Translated in another way, we can say that with too little stress, we tend to be bored. With too much, there tends to be anxiety, possibly burnout, exhaustion. So we need something roughly in the middle. As most laws in the world have always been challenged, they've been challenged in psychological science as well. So McClelland in the 1960s found a little problem with this, but it's not beyond our scope for right now. So this then gets us to the issue of resilience. And what is it in neurological terms? Well, resilience is our ability to cope with setbacks, adversity, trauma, and being resilient is necessary for us to be able to continue with life. But one of the misconceptions about resilience is that that we won't experience difficulty. Of course we do. It's what we do with the difficulty that's critical. And that's what dovetails with what the other speakers are going to be talking about later on, and what Dr. Mayer had spoken about previously. So resilience refers to how one manages difficulties of life and what skill sets are necessary for that to happen. And resilience helps us with our personal growth and gives us a better and newer perspective on life. Are we born with it? Maybe to some extent we are. But what we can say is, if we don't fix the chronic stress, we will wind up dead. Celia has shown that many times. Why? Because with chronic stress, you have an increase in fibrinogen level, blood clotting factor. So if you're prone to heart disease, you're very much more likely to throw a clot. But it's also related to respiratory stress, respiratory rate increases, heart rate increases, blood sugar level increases, pilomotor response, the hair on our skin increases, and we have a collective of things that the good Lord, in her infinite wisdom, says, well, I'm going to help you out here. If you are in a state of stress, prolonged stress, probably a good idea to get out of it. So if you don't do it yourself, I'm going to make you sick. And when you're sick, you're not going to be doing anything. If you're dumb enough to go to work when you have the flu, well, then the likelihood is that you're going to get a whole lot sicker and probably at some point wind up dead. So resilience then, in terms of what we've been speaking about, is highly associated with neuroplasticity. And that is when there was a limited or certainly a different awareness and understanding of mental health, it was thought that all human behaviors were innate. And I'm pushing this as a physiologist. And there were no ways to control those behaviors. So if a person is not resilient, there's no way to develop it. We don't think that way anymore. We now know that through neuroplastic changes, that is the ability of the brain to continually reorganize itself, both functionally and physically, resilience can be achieved. So neuroplasticity, in terms of what we're talking about, is how our brain can be trained to change and develop its neural networks by growth and reorganization. And that can be done very well externally. So these synaptic connections, the histologies of which I had shown you before, can be resynced by learning and rigorous training. What brain structures are involved in resilience? Well, without going to detailed lessons in neuroanatomy, there's one area of the brain in particular that's involved, and that's the amygdala. Amygdala, by the way, is highly active, preferentially active in teenage years, and that's why the car insurance rates for our teenage drivers are astronomically high. It disappears for males after the age of about 26 and for females at the age of about 23 because something happens. We, human beings that are neurologically mature, begin to start using our frontal lobes in order to make decisions and not the amygdala. Surprise, surprise, the amygdala actually gets seriously messed up as we get older. That's one of the reasons for problems with emotionality and things like that. When you marry this with a hippocampus, you've got short-term memory problems. But I'm not going to get into this in greater detail right now, given the time that we have. So the amygdala is part of the brain that's most responsive to emotional behavior. And any kind of emotional behavior triggered by the amygdala, we know that the neurons extend from the amygdala are triggered by stress and by fear. The existence of resilience by its very nature, that is our ability to cope, implicates neuroplasticity. So resilience involves the mechanisms that promote flexible adaptation to change. Allows us the capacity to persist towards long-term goals, independent of whatever's going on around us. Plasticity relies on the neurobiological systems that underpin social fitness, physical stamina, and endurance as individuals flexibly adapt to diverse conditions. Bonding between organisms, between animals, it can be non-human forms and it can be humans as well. Bonding is the process of getting the greatest degree of neuroplasticity in mammals, and there's a reason for it, and we'll be taking a look at that very quickly. Significant degrees of neuroplasticity has led to the evolution of what we call viviparity, which is internal gestation. Kangaroos, for example, or marsupials don't have viviparity. In addition, it also leads to physiological reorganization in mother and young that enable the maturation of the fetus within the maternal body. In fact, just as an aside for a few seconds, my principal area of applications research is not this. It's actually looking at the development of cognition and consciousness in the fetus. And we find that there are substances, hormones that are generated by the mother in response to the response of the fetus. So mother and fetus are interacting prior to birth. Birth is not the beginning of psychological or let's call it cognitive life. There are precursory issues to it and all part of development. And I'm not getting into a political debate on this particular subject. But significant degrees of neuroplasticity is necessary for us to get through the first year of life. What happens as a result of this bonding is that there is the involvement of the oxytocin system, which is key to the issue of neuroplasticity. It's critical to the formation of attachments also, mother-child relationships. Yes, daddy's involved too, but it's largely mommy. And the period after childbirth marks the time of greatest plasticity in the adult brain. Kids imitate, newborn infants imitate. If you stick your tongue out at a 1 week old neonate, the neonate will copy you. But they're already doing that in the womb.
Dr. Leisman, 2 minutes.
Okay, so moving right ahead. Resilience is integrative and regulatory. It's time-based. That is, it goes from simple to complex. And resilience is social, which means there's a reason that we have religious groups. There's a reason we have social and political groups, because they offer us support. And that support increases levels of oxytocin, which has something to do with bonding. If you think that being Italian, for example, actually exists, the answer is absolutely it doesn't. And the reason it doesn't is because in 1864, Vittorio Emanuele II was the king of Sardinia who organized the Italian city-states for the first time since the 7th century. There were no Italians before Vittorio Emanuele. So our need to bonding has a lot to do with building these kinds of circuits. Social synchrony is involved in this as well. So, in summary, the neural structures that cohere into the affiliative brain are formed during early sensitive periods in human development, allowing us humans to extend love to strangers, social groups, and abstract ideas. And cross-generational cultural myths or religious beliefs run the risk of overlooking the first tenet of resilience, which is flexibility. By tightening habits, obligations, submissive attitudes, and increasing surveillance and rigidity, you reduce the capacity. You reduce, I repeat, you reduce the capacity for resilience. The object is to create affiliations, religious or otherwise, with flexibility. Save that, it's not going to work. So, one last point before we finish. We studied the neural responses of Israeli and Palestinian youth using MEG, magnetoencephalography, while viewing in-group and out-group protagonist in pain. For the first 500 milliseconds, representing the brain's automatic response to vicarious pain, the youth responded to the pain in both in and out-group members. But after a half a second of grace, top-down brain processes blocked the brain's natural empathic response to the out-group, displaying only a response to the pain of the in-group. That's what affiliation is. So affiliation is very healthy, but you have to be really careful about what it is that happens with this. So the elements in summary, the elements of the behavioral functions of a healthy mind: awareness, connection, insight, and purpose, and they generate neuroplastic changes. Finally, this is the dynamic brain changes associated with stress. This is resilient coping, and this is risky coping. Clearly measurable objective differences in both. And finally, these are the changes of emotional regulation of various parts of the brain. All of that having been said, thank you very much, and toda rabba, muchas gracias, and shukran.